As a process that consumes up to 4% of global electricity and an efficiency less than 5%, sometimes less than 1%, comminution, or a process to reduce rock size to the point where minerals can be liberated, has been high on a list of problems to tackle in the mining industry. Existing comminution techniques break rock by applying impact, compression, and/or shear forces, using steel balls, rods, or other media, or surfaces that compress and impact the rock until they break. Back in 2019, we introduced a novel comminution technique we call Transcritical CO2 Pulverization, or tCO2 for short, that takes advantage of the weaker tensile strength of rocks instead of overcoming the stronger compression strength. By using the supercritical properties of CO2, we're able to pressure infuse the gas into the rock's pores to then rapidly release the pressure, causing the gas to expand inside the rock, effectively breaking it from within. This approach aims to significantly reduce the energy consumed during comminution, as well as deliver embodied energy and emission savings, since it does away with the consumable media needed for impact-based techniques. The first prototype using tCO2 pulverization was built at the end of 2019. We called it the Minimum Viable Experiment, or MVE. The MVE was a small manually operated bench apparatus, which proved that, indeed, we could break rock using the unique properties of supercritical CO2. The next step forward was building a second lab-scale prototype, taking the lessons we learned with the MVE to advance our understanding of the process and characterize the types of ores more susceptible to this new technique. This prototype, codenamed Alpha, is a more automated apparatus with a larger feed capacity and capable of operating at higher ranges of pressure and temperature. Stepping through one experimental tCO2 cycle, the feed material is first prepared and loaded into the Alpha, securing the removable cap in place. The software operating system is started, accepting a set of input parameters to control the machine over the test cycle. CO2 is loaded from a supply tank, and a hydraulic ram compresses the CO2 into the rock chamber, followed by heating to begin the high-pressure supercritical CO2 permeation process. After a few minutes, an ultra-rapid action valve opens, decompressing the CO2 into the expansion chamber, causing the rock to fracture. The system is then fully depressurized, and the rock sample is retrieved for size reduction analysis. Through the experiments run so far, we were able to learn some of the tCO2 process conditions that lead to comminution, and to associate these process conditions with a software energy model to calculate the estimated energy consumption for scaled-up operations. We have shown reliable comminution of industrial limestone used for cement production, and have observed comminution of harder metal mineral-bearing ores, which we have to now more fully quantify. Our current best calculated energy estimates put tCO2 direct energy savings in the range of 15 to 23% over a comparable sag and ball mill circuit for 2 different rock types with comparable feed and product sizes. This is without considering the additional approximately 30% savings that will come from eliminating use of grinding media and reduction of liner replacements. However, we have the reason to believe, and early supporting evidence, that the physics of tCO2 allows an even greater energy saving potential. While the figures we report are promising, there remain a significant number of process conditions to be fully understood if we are to realize the promise of the technology. A preliminary economic assessment of a commercial scale, 3,000 ton per day tCO2 plant in comparison to the comparable sag and ball mill plant and processed rock suggests an operational savings of $5 million US annually after the 4th year of operations. We are at the beginning of an exciting new phase in the development of this novel technology. We have started from scratch and have shown that tCO2 pulverization could be a feasible alternative to existing comminution methods. Nevertheless, we still have work to do in understanding the thermodynamic and physical forces that govern the process and to better quantify its energy-saving potential. Continued experimental equipment development and refined experimentation will enable us to obtain the data and knowledge we need as we drive towards the design of an optimized commercial-scale comminution circuit, starting with a pilot plant. Thanks to the early support of Natural Resources Canada, We've been able to secure private funding and are now in talks with major industrial players interested in seeing this technology being commercialized in the next few years.